Hello everyone, I'm Zixiao Zhang from Xidian University. It's my honor here to have this opportunity to introduce a method we use during the track of object detection in ViT 2021. The goal of object detection is to predict a set of bounding boxes and category labels for each object of interest. Recently, automatic and effective object detection plays an important role in scene parsing on UAV platforms. In this case, the main task is to predict the bounding boxes of objects of 10 predefined classes. For example, pedestrians, person, car, van, bus, truck, motor, bicycle, all-in tricycle, and tricycle. However, as shown in the pictures, drone-captured images have overwhelming characteristics, including dramatic scale variance, complicated background filled with distractors, and flexible viewpoints, which pose enormous challenges for general object detectors based on common convolutional networks. So, to deal with these problems, we proposed some targeted methods and strategies. To begin with, for drone-captured images with large-scale and complex scene, to improve the semantic discriminability and alleviate category confusion, collecting and associating scene information from a large neighborhood can be useful in learning relationships across objects. In this work, we introduced a multi-head self-attention block in the original backbone CSP.NET to bring more context information and learn more distinguishable feature representations. Here it is MHSA.block. To be specific, in MHSA.block, we use multi-head self-attention with n layers to replace n CSP bottlenecks, each of which consists of one 3x3 spatial convolution and one 1x1 spatial convolution. The structure of self-attention layer is described in the right figure. Objects from the drone-captured images vary a lot in sizes, so it's crucial to effectively represent and process multi-scale features. In this work, we present a simple yet highly effective weighted bidirectional feature pyramid network, BIFPN, for effectively cross-scale feature fusion. First, BIFPN adds an extra edge from the original input to output node if they are at the same level, in order to fuse more features without adding much cost. Second, while combining low-level and high-level features, BIFPN introduces learnable weights to learn the importance of different input features instead of simply summing up or concatenating, which may cause feature mismatch or performance degradation. In addition, we implement other effective strategies, including test time augmentation and weighted boxes fusion, to improve the detection performance. Test time augmentation is an application of data augmentation to the test dataset. Specifically, we create multiple augmented copies of each image in the test set, having the model make a prediction for each, then returning an example of those predictions. Copies of samples in the test dataset are created with some image manipulation techniques performed, such as zooms, flips, shifts, and more. As shown in the experimental results, after TTA operation, the performance of predicted boxes improved to a large extent. As we all know, combining predictions from different models generalizes better and usually yields more accurate results compared to a single model. In this work, we adopt an effective method for combining predictions of object detection models, weighted boxes fusion. In the experimental results, The combined predictions for the test dive dataset yield superior performance with MAP41. Here is our final network architecture. First, input the image into the MHSA darknet backbone to extract features for the detector. The feature maps are further refined with the aggregation network BFPN, which aggregates features from different backbone levels for different detector levels. Finally, YOLO detection head is employed to predict bounding boxes at 5 different scales. Experiments have also proven that these methods and strategies can indeed improve the accuracy, as many previous works show. Here are the results of our experiments. As you can see, after integrating multi-hide self-attention into the original CSP darknet, the total MAP results are significantly boosted from 35.43 to 37.56. And we can see there is a significant AP boost, particularly for small objects. These results suggest that self-attention has a big effect in detecting small objects, which is considered to be an important and hard problem for deploying object systems in the real world. For CNN-based deep networks, the high-level feature maps are of fairly low spatial resolution, which lead to the lack of unbroken information to localize and recognize the small objects. While small objects always show the co-occurrences of certain classes in images, which to some extent explains the reason why the transformer-based model, which focuses on global context information, is helpful accurately detecting small objects. Here is the realized comparison between prediction results from the original baseline and our transformer-based model. We can observe that our transformer-based model successfully recognizes the people on motors, while the baseline model wrongly classifies them into pedestrians. It suggests that the input backbone MHSA darknet is capable of extracting more differentiated features for object detection via multi-hide self-attention and demonstrates a stronger semantic discriminability to elevate category confusion. Finally, this is our team information. Thanks a lot for listening.